acceleration is the rest of it. Yeah, that's how I want to talk about it. Okay. Mumbling to myself. Okay, what we're looking at here is the gravitational field, or the gravitational field strength. In our class this year, we've been using this little g, 9.8 meters per second squared. And I told us that was just like a constant value. Since the very beginning of the year, we've been using it for nearly everything. And this might be the only time that I would have lied to you, because this value is not always a constant. It does change depending on a number of factors, primarily your location. The way we get this value of approximately 9.8 though has to deal with everybody's favorite equation, F equals ma. Okay, now this F equals ma works out just fine, but we also know that there's a specific form of this equation when we're talking about someone's weight, and it's that the weight equals the mass of the person, right? So this is like a person times g, gravity. Well, if that equation there is really just F equals ma, and we know that F equals ma in a gravitational sense is gmm over r squared, then what we can really say here is that the weight of the person is equal to big G times the mass of, well, one of the objects. And if we think about, my weight pulling down on me, what's also happening is I'm pulling up on the Earth. So the Earth, which remember is the symbol of just the plus, is one of our masses. And our second mass here is the mass of the person. And this all needs to be divided by, well, let's take a look. If here's the Earth, and you're standing here on the surface of the Earth, it looks like you're very tall, we just want, well, what is that distance from the core of the Earth up to you? What is the radius of the Earth? So we look at our best friend, and we say, what's the radius of the Earth? And it is a value of, let's see, that's our 6.38 times 10 to the 6th, but it's gmm over r squared. What we can do with this here is we're going to notice very quickly that the mass of the person ends up dividing out here. And we end up seeing that gravity, this little g, is equal to just g times the mass of the Earth divided by the radius of the Earth squared. And that would be the amount of gravity at the surface of the Earth. And if we plug in values for this, remember, universal gravitational constant is 6.67 times 10 to the negative 11th. The mass of the Earth is 5.97 or 96, depending on how you round that, times 10 to the 24th, all divided by the radius of the Earth, 6.38 times 10 to the 6th meters squared. If we go ahead and plug all of this into a calculator, and we got to be careful about this, if we did a quick back of the envelope, we could probably see that 24 minus 11 is going to give us 13, and then 6 squared is 12. So we're going to get a number here that's like times 10 to the first, which is really just like whatever number we get. So it's about the 9.8 of gravity. If we take a look at this, 6.67 times 10 to the negative 11th times the quantity of 5.97 times 10 to the 24th divided by 6.38 times 10 to the 6th squared, we get a value of 9.78 meters per second squared. 9.8. Technically speaking, if we average everywhere on the Earth, because not everywhere on the Earth has the same radius. Some regions of the Earth are in a valley, some are up high in the mountains. Then if we average all of those, we get an average around the Earth of about 9.81. Other things that matters are, what is the mass that's actually underneath you? Is it just loose sand and soil, or is it like a big iron chunk under you, or like a large iron deposit under you? Is it just water? What is it? But in general, that's how we figure out what gravity is at some location. And what we can also do with this, if you wanted to, is we could figure out for the astronauts way out here in space, what is the gravity out there? Because, you know, the astronauts are floating, right? So what happens if an astronaut is like 250,000 meters up into space? Well, what would their gravity be? You know, we might think that it's zero because they're floating, but as we're going to see momentarily, it's really not. We'll play the same equation as before. G equals G times the mass of the Earth. Remember, we saw up here that the mass of our astronaut, or the mass of the person, doesn't matter. That value cancels out each time. And when we divide this, we need to divide it by the distance between the center of our Earth and where the astronauts are squared. So when we do this, it's a very similar setup. 6.67 times 10 to the negative 11th times the mass of the Earth, 5.97 times 10 to the 24th. But when we divide this, we need to be careful. What we have here is not only the radius of the Earth right here, but we have to add that value to the 250,000 meters, which isn't that much distance, believe it or not, but it needs to be added in, and they both need to be squared. So if we do this, our radius of the Earth, as we said, is 6.38 times 10 to the 6th. We have to add to that 250,000, and then we can square that quantity. Okay? If we do this and we put that all together, maybe you'd like to add the denominator first. If I do 6.38 times 10 to the 6th plus 250,000, you end up getting for the denominator that, with the numerator being the same, 6.67 times 10 to the negative 11th times 5.97 times 10 to the 24th. The denominator in this case is, let's see, 1, 2, 3, 4, 5, 6. 6.63 times 10 to the 6th squared. So our denominator didn't change that much. We just added a little bit more onto that. And if we put all of this together to try to figure out what is the gravity for the astronauts kind of up in space on the space station, we notice we're probably not going to get that much of a change. These are actually pretty similar setups here, and our denominator really hasn't changed much. So if we do this, 6.67 times 10 to the negative 11th times 5.97 times 10 to the 24th, divide by 6.63 times 10 to the 6th squared, we see for our astronauts that the amount of gravity, or the acceleration due to gravity they have up on their shuttle, is 9.06 meters per second squared, which I guess brings up the question, how do astronauts float? I guess we'll have to see that at a later date. With that, though, you can find the gravity at any location around some object, and that kind of problem is finished.